So welcome to the video lecture series on Introduction to Computer Networks. This is part 5 of our lecture on Ethernet LAN networks. So we will jump off to the point where we left off. So, all right. So far, in the case of Ethernet LANs, we have seen that almost all of the functionality of the frame forwarding is dependent on MAC addresses. So layer 2, which is the link layer, needs to have some form of mechanism through which the hosts can learn the MAC addresses of its destinations. So for that purpose, the ARP, which is the short for Address Resolution Protocol, is a protocol which allows hosts to discover the link layer addresses, which is the MAC address. It runs in layer 2, that is the link layer, this particular protocol. Some places you will see that people say that it is a protocol which runs in between layer 2 and layer 3. That is between between the link layer and the network layer. And this is said because the protocol ARP runs in layer 2 but requires information from layer 3. However, the protocol itself is focused in layer 2. Something that should be clear with respect to ARP is that the protocol runs within the boundary of a single network. So if we have a complex network where we have multiple smaller networks connected, ARP can only run in one of the single network boundaries, and if it is across networks, ARP is not the one that is used. So it does not travel across other networks, and it is maintained within the boundary of a single LAN. The format of ARP maintains a very simple request and response format, and eventually the protocol allows hosts to learn the MAC addresses, which are then stored in something that we call an ARP cache, which is located on each of the hosts to maintain the addresses that it has learned. So first, the ARP request is sent out by a host, and it is in the format of a broadcast request. So what happens is that, for example, in this case, host A will send out the ARP request, and the request will be broadcasted to all the other hosts in this particular network. And the request states that host A is trying to find the MAC address of the host which has the IP address as shown here. For example, 141.23.56.23. So the broadcast request holds the information of the destination IP address and is requesting the MAC address of the host with this IP address. So when the request is broadcasted and reaches all the host which has the matching IP address will then send out a reply. So this is a unicast response, which means that it will travel directly to the host which was initially looking for the MAC address. So the reply holds the MAC address of B that initially host A wanted to know. So in this example, let's say host Argon with an IP address of 128.143.137.144 IP address and the following MAC address would like to know the MAC address of router 137. So the ARP request that is sent out from Argon states these four fields. The source MAC is the MAC address of Argon. The source IP is the IP address of Argon. The target IP is the IP address of the host that Argon would like to know. However, if you see here, the MAC address, the target MAC address in the request is set to all zeros, which means that whenever there is an ARP packet where the MAC address is set to all zeros, the protocol will understand that this is an ARP request. So eventually, what happens is that this request is sent out to all the nodes which are connected to the same network. And eventually it reaches router 137, which has the IP address that is stated in the target IP of the ARP request. So router 137 will then send out an ARP reply with the same four fields. It will have the source MAC, the source IP, the target MAC, and the target IP. So here, the source MAC will be the MAC address of router 137. The source IP will be the IP address of this router. The target MAC is extracted from the ARP request, and the target IP is also extracted from the ARP request. So at the end of this protocol, the host, Argon, will get to know the MAC address of router 137. So when hosts are running the ARP protocol and learning the MAC addresses of the hosts which are connected in this network, it sends out these ARP requests and responses. However, if each of these hosts are learning the MAC addresses for each IP datagram or IP frame every time it wants to send out, it kind of runs into this overcrowding of requests, and it's not really an efficient solution. So this is where the concept of an ARP cache comes into play. The idea is that each host will maintain a cache, which is basically a table of records for all the MAC addresses it has learned over the past 20 minutes. The time can be changed and can be configured, but this is kind of like the standard measure of time that we have for the ARP protocol. So a sample of the ARP cache looks something like this, where the ARP cache for a host can have the IP address and the MAC address paired like this. And it's just a list of IPs and MACs listed one after another. So whenever a host is actually trying to send out a frame, it needs to know the MAC address. So for that, it just goes through a resolution logic. So first, it sees that is the destination MAC address known. So it sees that if it is required that we resolve the MAC address. If it is no, it just ends the ARP protocol. If we see that the resolution is required, it checks if the result is already in the cache. If it is, and it has not expired yet, it will then get it from the cache and end the ARP protocol. If the result is not in the cache, it will then run the ARP protocol, and if the process is successfully completed, it then stores it in the cache and ends the protocol. However, if it fails to run, that means if that particular IP is not present in that network, so it will fail to resolve the MAC address for the given IP, and in that case it just returns an error and ends the process.